Bismillahirrahmanirrahim. Assalamu alaikum. Today is our 7th lecture. Okay. In this lecture, we will start from multiplicative functions. Multiplicative functions. Okay. So before going towards multiplicative functions, let me define number theoretic functions. Okay. So before going to the definition of multiplicative function, so this is definition of number theoretic function. Number theoretic functions. Okay, so definition: a function that maps the positive integer into a set which is closed under a product is called number theoretic function, called a number theoretic function. Okay. For example, we discussed in last class about Euler function phi. So function phi is a number theoretic function because we apply phi on positive integers. For example, we apply phi on 6. So then we find the numbers which are relatively prime to 6. So 1 and 5 are relatively prime to 6. So phi of 6 is 2. Okay, so we apply this number to positive integers and we get the results in the set, means natural number which is closed under the product. Okay, so these number theoretic functions are of two types. Okay, or we usually consider two types of multiplicative number theoretic function. One is multiplicative functions. So a number theoretic function f is called multiplicative. Let me use different color. Okay. Multiplicative if GCD of m and n is 1, implies f m times n equals f of m times f of n. So if we have this type of property in any number theoretic function, then that number theoretic function is multiplicative. The second type is completely multiplicative. Completely multiplicative so a number theoretic function, a number theoretic function G is called completely multiplicative completely multiplicative if G of m times n is equal to G of m times G of n without any restriction, without any restriction of GCD, without restriction. Okay. Okay. Let me give an example for multiplicative functions. Okay. For example, f to the f of n equals 1. Okay. So that's the definition. So this is multiplicative, multiplicative since f of mn is 1 and f of m is also 1 and this is equal to f of n. So f of m times f of n equals f of mn because 1 times 1 equals 1. So f is multiplicative. Okay. Similarly, uh, for example, we have another example. G of n. G is a function. G of n is n to the power k. So this is another function where k is a fixed integer, where k is a fixed integer. So G mn equals mn to the power k, which can be written as m to the power k times n to the power k, and this can be written as f g g of m times g of n. So it means g is multiplicative. and all of them are number theoretic functions. Okay, so let me introduce a result. Theorem 1. Let f be a multiplicative function and n a positive integer with canonical decomposition n equals p1 e to the power 1 p1 to the power e1 times p2 e to the p2 to the power e2 till pk to the power k ek. Then fn equals f p1 to the power e1 times f p2 to the power e2 till f p k to the power ek. Okay, and canonical decomposition means prime factorization. For example, if we have a number 40, so its canonical decomposition is 2 cube times 5, because 2 cube is 8, 8 times 5 is 40. So this is canonical decomposition. For example, for 36, we write 2 square times 3 square. So that's the canonical decomposition of 36. Okay, means prime factorization. Okay, look at the proof of theorem 1. Okay, we will prove this by induction. So for induction, we take k equals 1. Okay, so when k equals 1 means then n equals p1 to the power e1. In this case, this implies f of n equals f of p1 to the power e1. Okay, so theorem is trivial. Okay, in this case, theorem is trivial. So the next thing, for induction, we assume a statement is true is true for k. Okay, that is f n equals f p1 to the power e1 times f p2 to the power e2 till f pk to the power ek. And we have assumed that this statement is true for k. Now we have to show that this statement is also true for k plus 1. Okay, when we take k plus 1, so we assume that let n be any integer with k plus 1. If we assume that this statement is true for k, it means we assume that n has k factors. Okay, n has k prime factors. Okay, to k distinct prime. So if we assume let n be an integer with k plus 1 distinct primes in canonical decomposition or prime decomposition or prime factorization, any word you can use here, decomposition, say n equals, so now n equals f, any prime decomposition is n equals p1 to the power e1 times p2 e2 till pk ek times p k plus 1 e k plus 1. Okay, and we have already proved result uh, for k. So this can be written as fn equals f p1 to the power e1 times f p2 to the power e2 till, and you can write here pk e to the power f of pk e to the power k times p, sorry, this must be k plus 1, pk plus 1 e to the power k plus 1. Okay, and because these are all distinct prime, so the GCD of product pk e to the power k pk plus 1 e to the power k plus 1 with the other is always 1, because all of them are relatively prime due to prime factorization. Okay, now the other factors will remain same, f p1 e1 f p2 to the power e2 till, and now look at these two values. You can consider this as m and this one as n. So f is multiplicative because it's given here in the theorem, and we know that pk e to the power k and pk plus 1 e to the power k plus 1 are relatively prime because their GCD must be 1. Okay, because they are distinct prime. So pk and pk plus 1 are distinct prime. So their parts must be distinct prime. So if they are distinct prime, so their GCD must be equal to 1. So if the GCD of these two numbers are, if the GCD of these two number is 1, then this can be written as, and the function is multiplicative. So we can write ek times f p k plus 1 e to the power k plus 1. Okay. So we assume that this statement is true for k factorization. Now we have proved that this product or statement is true for k plus 1 factorization as well. So by the principle of induction, this statement is true for any integer, any positive integer n. So statement is true for any positive integer. Okay. Okay. Let me introduce another result. Okay. Better to use a different space. Okay. Theorem 2, for example. Let P be a prime and E any positive integer, then okay, E is any positive integer and P is prime, then phi of P to the power E is P to the power E minus P to the power E minus 1. And phi is Euler function that we have already discussed in the last lecture. Okay. Proof. So what is phi? P to the power E. So number of all positive integers less than or equal to P to the power E and are relatively prime to it. So this is equal to number of positive integers I think it's better to write is number of positive integers less than or equal to P to the power E and relatively prime to it. Okay. Now we have to find those numbers which are positive integers less than or equal to P to the power E and relatively prime to it as well. Okay. So, and we know that P is a prime number and phi of P is P minus 1. Okay. So now, so we consider is the number of all positive integers less than or equal to P to the power E. Okay. And relatively prime to it and relatively prime to P to the power E as well. So we consider number of positive integers less than or equal to p to the power e. Okay. One thing, number of positive integers less than or equal to p to the power e. Okay. But we don't know, but we don't want all positive integers. Okay. So we have to exclude which are not relatively prime to p to the power e. Okay. So there are two types of positive integers less than or equal to p to the power e. One of them are relatively prime to p to the power e, and the other types are related to which are not relatively prime to p to the power e. Okay. So the other type is number of positive integers less than or equal to p to the power e and not relatively prime to p. Okay. So prime to p to the power e. Okay. So these type of numbers can be computed. Okay. How can we compute it, these type of numbers? Number of positive integers, okay, number of positive integers less than or equal to p to the power e and not relatively prime. They are all multiples of p. Okay. So you can you can count them. One of them is p, which is not relatively prime to p to the power e because their GCD must be p. 2p, similarly 3p. Okay. And we have p to the power e. So then you can count them till p to the power e minus 1 times p. Okay. Because all numbers till p to the power e, so the number comes before p to the power e is p to the power e minus 1. This is the with respect to coefficient. This is p to the power e divided by p. Okay. So how many of them? How can you count them? So this coefficient is 1, 2, 3 till p to the power e minus 1. So they are p to the power e minus 1. Okay. So p to the power e minus 1 numbers are not relatively prime to p to the power e and less than p to the power, less than or equal to p to the power e. Okay. So, and number of positive integers less than or equal to p to the power e. So p to the power e, because if you start from counting, you start and the total number, the total integers till better to use up to p to the power e are 1, 2, 3 till p, then again 1p, then 2p till, and the last one must be p to the power e. So this is the total number, and these are the numbers which are not relatively prime to p to the power e. Okay, so you need to find the numbers which are relatively prime to p. So it means you can write phi of p to the power e is equal to p to the power e minus p to the power e minus 1. Okay, and okay, that's the proof of the theorem, and this can also be written in a different way. Phi p to the power e is equal to p to the power e minus p to the power e over p. Okay, so you can write p to the power e times 1 minus 1 upon p. So phi of p to the power e is p to the power e times 1 minus 1 over p. Okay, we usually write like that. Okay, let me give an example. For example, phi to the power 81. We know that 81, because it's very difficult to find all numbers which are relatively prime directly in a direct way, that all numbers which are relatively prime to 81 and less than or equal to 81 and relatively prime to 81. But by using the above theorem, we can easily find, because phi can be written as 3 to the power 4. So p is 3 here and e is 4. So this must be 3 to the power 4 minus 3 to the power 3. So 3 to the power 4 is 81 again, and 3 to the power 3 is 27, which is 54. So 54 numbers. Okay, or if you use a different formula, so but it's very simple. You can use this formula, or you can use 3 to the power 4 times 1 minus 1 upon 3. Okay, so this is 3 cube times 2, which is 54 again. Okay, before going to more example, okay, let me give an example that shows that phi is a multiplicative function. Okay, phi is a multiplicative function. For example, if we take okay, for example, we take phi of 4. We know that phi of 4 is 2. Then phi of 7, because 7 is prime, so 7 minus 1 is 6. and phi of 28. So 28, phi of 28. So phi of 28 is 12. Okay, you can count numbers which are relatively prime to 28. So there will be 12 numbers. So phi of 4 times phi of 7, which is 2 times 6, which is 12, and this is equal to phi of 12. So, but this example shows that. So, through this example, you can only verify that you can verify that phi is, but phi is a multiplicative function, but that's not the general rule of proving the result that phi is multiplicative. So, in general, we have a theorem that theorem 3, okay, the function phi is multiplicative. Okay. At this stage, I am skipping the proof of this theorem that phi is multiplicative, but we can use this result to show some other results as well. For example, we have another result. Let n equals p1 to the power e1, p2 to the power e2 till pk e to the power k be the canonical canonical let n be the canonical decomposition of a positive integer n, then phi n equals n times 1 minus 1 over p1 times 1 minus 1 over p2 till 1 minus 1 over pk. Okay. Okay. Now move to the proof. We know that phi is multiplicative, it's given here, and p1 to the power e1, p2 to the power e2, and all of them are relatively prime. And by using our first theorem that we discussed today, so phi n can be written as phi of p1 to the power e1, phi of p2 to the power e2 till phi of pk to the power ek. Okay. Now, by using the second theorem that we discussed here, phi of p to the power e. Okay. So phi of p to the power e is p to the power p1 to the power e1 minus p1 to the power e1 minus 1 by using the result given here. Okay, so that's the result which is being used in our current theorem. So this bracket, then we have p2 to the power e2 minus p2 to the power e2 minus 1 times pk to the power ek minus pk to the power ek minus 1. Okay. Now, this can be written as p1 to the power e1 minus p1 to the power e1 divided by p1. Okay. And then in the next bracket, we can write p2 e2 minus p2 to the power e2 divided by p2 because we have power minus 1 here. So that's why we can write like that. Still, we can write pk ek minus p to the power k ek divided by pk. Okay. Okay. So in each term, we see that pi's are common. Okay, so we can in each factor, I think. So p1 can be taken as common. P1 to the power e1 can be taken as common from the first factor. So first factor will be 1 minus 1 over p1, and then p2 can be taken. P2 to the power e2 can be taken as common from the second factor. So 1 minus 1 over p2 till pk to the power ek is common from the last factor. So this is 1 over pk. Now we can write all p's together. So p1 e1, p2 e2 till pk ek times 1 minus 1 over p1 times 1 minus 1 over p2 till 1 minus 1 over pk. Okay, now this product is given as n here in the result. So n times 1 minus 1 over p1 times 1 minus 1 over p2 times 1 minus 1 over pk. So this is very useful formula. By using this formula, you can find phi of any number which is not prime as well. Okay. For example, let me give an example. Okay. For example, n is 1976. So phi of 1976 can be factorized as 2 to the power 3, 13 to the power 1, 19 to the power 1. Okay. So phi of 1976 is 1976 times 1 minus 1 over first factor, first prime, which is 2, then 1 minus 1 over second prime, which is 13, times 1 minus 1 over third prime, which is 19. Okay. Now, so this is 1976 times 1 over 2 times 12 over 13 times 18 over 19. Okay. So when 1976 is divided by 13, 19, and 2, so this gives you 4. Okay, because 2 cube here, so this is 4. So 4 times 12 times 18 is 864. So this is 864. So this is very easy procedure to find the phi of any number. Okay. Okay, let me describe the procedure of sums through the divisors. Okay, because we are pretty much familiar with the summation sign. Okay, but like for example, if we have something like fn and we write n equals 1 to 4, so this is same as f of 1. So we put n equals 1 here. So f1 plus f2 plus f3 plus f4. We can use some exceptions here as well. For example, if we use sum n is equal to 1 till 4 and n is not equal to 2, fn. So in this case, we omit n equals 2 here. So this will be f1 plus f3 plus f4. Okay. But now the sum that I want to or I'm showing here, it is little bit different. Okay. So I'm showing here a summation sign. Okay. And here, for example, we have D. Okay. So here n runs through 1 to 4 and here n runs through 1 to 4, but excluding 2. So f of d is a function, and now we need d runs from some point to some point. So here we write d divides 12. So d runs through divisors of 12. Okay, so divides 2. So d is the number which divides 12. So 1 divides 12. Okay, so f of 1 should be written here. Okay, and 2 is a divisor of 12 because 2 divides 12. So the value of d is 2 now. 3 divides 12. Okay, so 3 can be taken here. So f of 3. 4 divides 12. Okay, so 4 can also be taken. But 5 does not divide 12. So you can't take f of 5 here. But 6 divides 12. So value of d can be 6. So we can take f of 6 here, but 7 does not divide 12, 8 does not divide 12, 9 does not divide 12, 11 does not divide 12, 10 does not divide 12, and means completely divide. Okay, but 12 completely divides 12, so f of 12. So d can be taken as 12 as well. Okay, so in that case, if we define a function on the basis of divisor, if we have a summation on the basis of divisor, so if d runs through the divisors of any integer, okay, then if f is multiplicative, then the sum is also multiplicative. Okay, so we can verify this by example, as well as we can prove in general that the sum is uh, multiplicative. Okay, so I'll give some example, and after that example, I'll show that the sum is multiplicative as well. Okay, hopefully in the next class. Okay, but today I'll show with the example that the uh, example that the sum is also multiplicative. Okay, so we define a summation. Sum runs through the divisors of n over the function f of d, where d is a divisor of n, and f is a multiplicative function, and this sum is, for example, is represented by capital F n. Okay, so if small f is multiplicative, then capital F is also multiplicative. Okay, so we assume that, so this is a result, and we will prove this result inshallah in next class. Okay, so today I'll give an example that will show that the sum is also multiplicative. Okay, and f is multiplicative. This is our assumption here. Okay, so for example, let m, so I'm giving an example only. So m okay, okay, so this is an example. We take for the example, we take m equals 4 and n equals 7. Okay, so 4 times 7 is 28. Okay. So first we will compute F28. So F28, we are using the product 4 times 7. You can also take the product 2 times 14. Okay. So f of 28, so this can be written as, and we have assumed that f is multiplicative. Okay, so divisors of 28 of f of t. Okay, so this is f1 is a divisor. Okay, 2 is a divisor. Okay, 3 is not a divisor. 4 is a divisor of 28. Good. 5 is not a divisor. 6 is not a divisor. 7 is a divisor. So f of 7. 8 is not. 9 is not. 10 is not. 12 is not. 13 is not. And 14 is a divisor of 28. So f of 14. And then f of 28. Okay. So that's f28. Now compute f4. Okay. So f4 is divisors of 4 f of d. So divisors of 4 are f of 1, okay, plus f of 2 plus f of 4, because 4 is also a divisor of 4. Then f of 7. So there are only two divisors of 7, which are 1 and 7 itself. So we can write f of 1 plus f of 7. Okay, let me write bracket here as well. Okay, now multiply f of 4 times f of 7, and we will prove that this will be equal to f of 28. Okay, but in general we will prove in next class, inshallah. So f of 4 times f of 7. So f of 4 is f of 1 plus f of 2 plus f of 4 times f of 7, which is f of 1 plus f of 7. Okay, so this can be written as f of 1 times f of 1 plus f of 1 times f of 7 plus f of 2 times f of 1, okay, plus f of 2 times f of 7 plus f of 4, because we are multiplying. Okay, now f of 4 will be multiplied with f of 1 and f of 7. So f of 4 times f of 1 plus f of 4 times f of 7. We know that f is multiplicative, so f can be written as f of 1 times 1 plus f of 1 times 7 plus f of 2 times 1 plus f of 2 times 7, then plus f of 4 times 1 plus f of 4 times 7. Okay, because it's multiplicative. So now f of it's f of 1 plus f of 7 plus f of, and let me rearrange them as well. So f of 2 times 1 is a f of 2. So let me write f of 2 first. Then f of 4 times 1 is f of 4. So let me write f of 4 here. So we have done with this one, we have done with this one, we have done with this one, and then plus f of 1 times 7 is f of 7. We have done with this one, and then in the last, f of 4 times 7 is f of 28. Now, this is same as F28. F28 means F 4 times 7. So F of 4 times F of 7 is same as F of 4 times 7. So it means F is multiplicative. Okay. So this is only an example. This example doesn't show, this example only shows that for particular value 28, that this function f is multiplicative, but inshallah in next class we will show that function f is multiplicative for all integers if f is multiplicative. Thank you. Allah.